Hello, everyone. In this video, I am going to go over Chapter 4, Section 2.1, Scalars and Vectors, Section 2.2, Vector Operations, and Section 2.4, Additions of a System of Coplanar Forces. Starting with 2.1. 2.1 gives you the definition of scalar and vector. How are they different? Typically, when we talk about scalar, it means something that has only magnitude but no direction. For example, if we say the mass of something, a mass of a box of books, okay, there's no direction. If I say temperature of the day is 72 degrees Fahrenheit, there is no direction. There's only magnitude attached to this physical quantity. Then it is a scalar. Now, if there's something that we need to define the magnitude in the direction of this quantity, and it will be a vector. For example, forces, right? 5 newtons of force. Is it pulling down? Is it pulling up? Direction of the forces does matter when the direction of the physical quantity does matter. It's a vector. Velocity is another example. I'm driving 60 miles per hour on I-10 toward San Antonio, going west, so the direction west. Or if I'm going 60 miles per hour going east, magnitude is the same. They both are 60 miles per hour. But in order to define the velocity, you also need to define the direction. Which way are you going? So velocity is a vector quantity. Okay, so in summary, scalar is something that has only the magnitude. Vector is magnitude plus direction. Section 2.2 start talking about vector operations. So for example, on the screen, we have vector A. Okay, we have a vector A, starting with the A. 2A will be magnitude 2 times of the original vector A. Okay, but still, they're following the same direction as the A, but the magnitude is 2 times as the original vector A. And then the third one, if I have negative A, my magnitude is the same. However, direction is going the total opposite, 100-degree opposite of my original vector. So starting with A, and then 2A is magnitude times 2, direction's the same. Negative A will be same magnitude, so the arrow is drawing the same length, but then the complete opposite direction because I'm doing the negative of the vector A. And then the last one, I have 0.5, negative 0.5A. Magnitude is half of the A, half of the original one, magnitude half. And then direction, since it's a negative value, you go in the opposite of the original direction of A. Okay. We're also in the vector addition, we're going to talk about either using the parallelogram law or the triangle method. Essentially, they're the same thing, but parallelogram law says that I have 2 vectors, vector A and vector B, and I need to put them together. Okay, when I say put them together, meaning I need to do addition of those 2 vectors. Since they're vectors, it's involving magnitude and direction. That means you cannot do a simple algebraic addition. When I say algebraic addition, it's like 3 plus 5 equals 8. You cannot do that because they are vectors. So simply you cannot put on just the simple numerical version together because they have a different direction. Vector A is going in a direction. Vector B is going in a different direction. What you do in the parallelogram law says that I am going to put the starting point of vector A and vector B together, putting the same starting point, vector A and vector B, and then start at the ending point of vector A. Start at the ending point of vector A. I am going to draw a parallel line. I am going to draw a parallel line. This line is going to be parallel to the vector B. Okay, the blue note over here. Start at the ending point of vector A. I am going to draw a parallel line that is parallel to the vector B. Same thing, start at the ending point of vector B, let me draw another parallel line. That parallel line is parallel to vector A, okay? Okay, so these two parallel lines that I drew, where they meet at the end, gives me the ending point of the sum of the vector. Okay, start at the starting point. Starting point, no, it's still the same. Starting point still the starting point of vector A and vector B, but then the ending point of the two parallel lines that we just drew is going to be the ending point of the resultant vector where A plus B is. Okay, so this one starting the green to cross two green locations, starting point and the ending point, if I connect them together, that will be the resultant vector of A plus B. That's what the parallelogram law says. The triangle method says, well, I have two vectors, it's still vector A and vector B. If I want to do the triangle method, we're going to call it the tip to tail. What does it mean? It means that I am going to start with one of the vector, let's say starting with vector A, okay? Vector A, I drew it. And then start at the ending point of the vector A, I am going to draw my vector B. Okay, start at the ending point of the vector A, I am going to draw the vector B. Now, after you finish your vector B, connect the starting point and the ending point. That gives you the resultant vector R. That gives you the resultant vector R. So same thing. Now, what the next diagram here is showing you that there's no order. You can also start with vector B. Start at a point, your starting point, start with your vector B. At the ending point of vector B, you draw your vector A, okay? Once you've done with your vector A, connect the starting point and the ending point together. That gives you the resultant vector. Either way, they will give you the same result for the resultant vector, okay? Let's keep going. Any questions, let me know. Next one that talks about the resolution of a vector is breaking up a vector into the component. This is sort of like the opposite, the reverse of the parallelogram. So in other words, resultant force F is given to you first, and then I'm going to break them into components. Okay, Fu and Fv, they are two components of the resultant vector F. Okay, remember it's vector addition, not algebraic addition. In this diagram, the one in the middle, the B diagram, diagram B shows you the parallelogram, and then the diagram C shows you the triangle. Next one over here, addition to the system of coplanar forces. This is section 2.4. This is saying that, well, giving me in vector F, I am going to break my vector into horizontal component and the vertical component. So in other words, I'm going to project the F into horizontal component Fx and the vertical component Fy. And a lot of times we call the Fx component being the I component along the x-axis, and also the Fy component being the j component along the y-axis. So here are two examples breaking down the force vector F into Fx and Fy. Okay, so the second diagram here shows you that, well, sometimes your X may not be truly horizontal and your Y may not truly be vertical. So, but we could still break them, right? X and Y axis are always, but X and Y axis are always perpendicular to each other, and together they can be set in any condition. If we need to adding vectors together, and there are multiple, in this example, you have F1, F2, and F3. If I need to add these three vectors together, what do? And keep in mind that when we're adding these three, F1, F2, and F3 together, they are not simple algebraic addition. They are vector addition, okay? What we do, first step, every single one of the force vector, F1, F2, and F3, we are going to break them into the horizontal component and the vertical component. So in other words, your F1, let's look at F1 only. Looking at the F1, we're breaking the F1 into F1x and F1y, horizontal component and the vertical component. We're doing similar thing for the vector F2, breaking that F2 into horizontal component F2x and the vertical component F2y. And then lastly, there is the F3. We're breaking it into the horizontal component F3x and the vertical component F3y. Okay, we're going to break every single one of the forces into the horizontal component and the vertical component. Now, next step, we can add all the horizontal component together. So there's your x, all the x go together. You have your F1x, F2x, and F3x. And you can simply, truly algebraically add them together because they are all on the same direction. Okay, so all the I component, adding them together, that's where that is. F1x, F2x, and F3x. And now when I say add them together, be careful with the direction. F1x and F3x going to the right. They both are positive. F1x positive, F3x positive, and F2x pointing to the left. You have a negative value. That's why F2x is left, because it's going to the left. Similarly, you're doing for all the y component. You have your F1y, F2y, and F3y. And again, adding all of them up together, but be careful with the direction. F1y, F2y is going up, and F3y is coming down. That's why you have a negative F3y. Be careful with the direction. Adding them together, you have a I component overall, horizontal component overall, and you have a vertical J component overall, resultant component X and resultant component Y along the I direction, along the J direction. Okay. Now, putting them together using the Pythagorean theorem, you have the X component overall. Remember from the last slide, we talked about you have FRX, horizontal component, FRY, vertical component, right? Putting that together, I can, using the Pythagorean theorem, I can know the magnitude of the resultant force overall, because I know the X component and I know the Y component, right? And then using the Pythagorean theorem, I can find out how what's the magnitude on the diagonal. And then I will do a tangent inverse. I can do a tangent inverse to find out what's the angle, okay? If this tangent inverse confuse you, you might could take a look at this shaded triangle, the green shaded triangle that I highlighted here. In this green shaded triangle here, tangent of theta equals FRY divided by FRX. This is, tangent is opposite over adjacent. And your opposite is going to be this part, right? The vertical part. And the vertical part is the same as, is equivalent to your FRY, right? So opposite over adjacent. Adjacent is this part, is your FRX. FRX is the adjacent of that triangle, adjacent side of that triangle, adjacent of that angle theta. So FRX over FRY. So if you do a tangent inverse, that will give you the angle theta here. All right, let's take a look at an example with some numerical value more specifically. I have three forces attached to this to this ring right here, F1, F2, and F3. Now we need to find the magnitude and angle of the resultant force. Again, three forces, they are vectors. If I need to do vector addition, it's not simple algebraic addition. If you do 300 plus 600 plus 450, that's not correct because they're force vectors. They are vectors. They have magnitude plus direction. What we got to do is every single one of the forces, F1, F2, and F3, we need to break them into horizontal component and vertical component. Okay, so F1, we're breaking it. So step number one, breaking. When we're breaking F1, it is vertical only. It has only vertical component because it's along the y-axis. That's why you have 0I and then 300J. Okay, all of the 300 Newton goes to the y component, projected to the J-axis. For your F2, it's 45 degree on the second quadrant. So when we're breaking our F2, you can do this way for your X component and this way for your Y component. Okay, so let me put an arrow over here and here. Okay, we're breaking it into this triangle or this parallelogram, or this will be a square case because it's 45 degree. Now, X component is going to be negative. Be careful, X component is negative because I'm going toward left. And your Y component is positive because I'm going up. Negative X, negative I component, and positive J component. And since it's 45 degree, your both of their magnitude, horizontal component and vertical component, their magnitude is the same. They both are 450 times cosine 45 degree or sine 45 degree, same thing. And then next one is my F3, okay? If you get confused with what's this 3, 4, 5 doing, this 3, 4, 5 triangle here tells me how slant this F3 vector is, okay? It tells me how slant this angle is. What it means is that when I break my 600 Newton force into the diagram, if I need to break it, let's see. So let me put a diagram on the side. If your F3 is over here and you're breaking your F3 into horizontal component, which is F3X, and then the vertical component F3Y, if I'm breaking them this way, based on the 3, 4, 5 triangle, which tells me how slant your angles are, what it means is that the vertical component is going to be 4, and then the horizontal component is going to be 3. Okay, to be more specific. So I have 3 is the horizontal. That's corresponding to your FX horizontal. Look, hold on, let me finish writing them. And then 4 is the vertical, which is the Y component. And then the 5 will be the F3, the diagonal. Okay, so let me color code it. Horizontal component is the 3 and the 3X. There's your horizontal. Vertical component is going to be your 4 or the 3Y. This one is F3Y. That one and that one's the same thing. So this is your vertical component. And then your proportion, lastly, let me use black. You will have the 5, which is corresponding to the diagonal of F3 together. Okay, horizontal, vertical, diagonal is proportional with this 3, 4, 5 triangle. Now, after we break them also, if this thing, if I keep writing, so where does this really comes from? If I keep writing, what it will look like is, let me see, hold on, let me use a good color. Let's go with black. So 3 over Fx equals, out of all this Fx and Fy, we don't know how much that is. That's what we're looking for. But then F3, we know the diagonal, we know is 600 Newton. Okay, so plug it in. 3 over Fx equals 5 over 600 Newton. That means in this equation, your Fx is going to be 3 over 5 times 600. I will let you look at the algebraic part yourself. And similarly, if I want to do the Y component, let me make some room over here. Let me move this. Okay, there you go. So over here, if you have 4 over Fy equals 5 over 600, right? The second part, we're looking for Fy, and then F3 we know is a diagonal, which is a 600 Newton. That means your Fy is going to be 4 over 5 multiplied by 600. Okay, putting that together numerically, I will let you put that in the calculator. That will give you the horizontal component or the I value of your F3, and then the vertical component, which is the J value, J component of your F3. Hope that helps you. Now, After we're done, right? After we're done, we are going to put all the I together. Again, let me color code it real quick. Next slide, what we're doing next slide is putting this I, and this I together, or putting all the I's together to gives you the I component of the force vector. And then the J, and the J, putting all the J together to give you the Y component or the J component. That's what we're doing on our next slide. And then overall, this is going back to, if I have the horizontal component of my resultant force, so in other words, this is my FX, FRX, right, or resultant force X component, and this one is my resultant force Y component, and putting that into a triangle using the Pythagorean theorem, that will give me overall what is the magnitude of the hypotenuse. And then do a tangent inverse. Again, if you needing additional help with the trig functions, you're looking at this shaded triangle. Find it, and remember I say horizontal component and the vertical component. You do tangent psi. Tangent psi is this angle right here. Tangent psi is going to be opposite, which is Fy. Fy over Fx, opposite over adjacent, okay? And then being said, if I know Fx and Fy, then it's actually resultant X and resultant Y. Resultant Y over resultant X gives me the tangent psi. And then if I do a tangent inverse, that will give me the angle, the direction, okay? So magnitude and direction. Example number 2. What we have the force being applied to this point right here. And we want to resolve the force into component along the U and V axis. And notice that in this problem, when we resolve them, U and V are not perpendicular to each other. So be careful. We're going to, a little hint over here is that we are going to use the law of sines. And let me show you how. Well, I have this 30-pound force, right? When I break that 30-pound force along the U axis and along the V axis, meaning we are going to draw a parallelogram, okay? Draw a line, start at the ending point of the resultant force, which is right here. We're going to draw a line that is parallel to V, okay? V is right here. Let's draw a line that's parallel to V, okay? And same thing for your U. Start at the ending point, pass through the ending point of the resultant, the overall force. We're going to draw a line that is parallel to U. So you have that one and that one parallel. You may look at this whole thing as a parallelogram. You may also looking at this triangle only, which is this one down here, okay? Where does the 45 degree, 30 degree comes from? Let me show you. Let me clear that out. Okay. So 30 degree comes out from, we know this angle is 30 degree, which is labeled right here, right? And we know that this line and this line are parallel. If this angle is 30 degree, that means this angle is 30 degree. That's where this angle 30 degree comes from, okay? Next thing is the 45 degree. Where does it come from? We know that when you're needing to decide the 45 degree, we know that this is perpendicular to each other, okay? There's your 90, okay? If we're looking for this angle right here, let's call it X, okay? Because the two red lines that I drew here, they're perpendicular to each other. That means 15 plus X, 15 degree plus that X degree plus that 30 degree will equal to 90 because they're perpendicular. And you're solving for the value of X should be a 45 degree. Okay, so that's where that 45 comes from. And then 180, we know, 45, 30, and then we can calculate because these three together needs to be 180. That means this one right here will be 105. Okay, so that's where all that angle comes from. And then in this triangle, if we're looking at this triangle only, the one on the top is your U component, and then this side of the triangle will be a V component. So that's where that comes from, FU and FV with all those angles. Using the law of sine, a quick review. A lot of science says that in a triangle, if I have side A, angle A, angle B, and angle C, and the opposite side of angle A will be this length side A, and then opposite side of angle B will be your side B, and then opposite side of angle C will be my side C. A lot of science says any triangle, this applies to any triangle. It does not need to be a right angle triangle, any triangle. It can be any triangle. A over sine A equals B over sine B equals C over sine C. And the triangle that we just break through for our U component and V component, we know all the angles. We already figured out all the angles. We can do all the sines, sine 105, sine 45, and sine 30, okay? And then the magnitude, the side, we know that the force that we are being applied, the force that being applied is 30 pounds, okay? We know that 30 pounds there for the one side of the triangle. And then we can solve for the value of U and FV. Either you're using this portion together or you're using that portion to calculate the value of FU, or you can do that one and that one together to calculate the value of FE, okay? Next thing is, let me keep going. Next thing is the group problem. Now, normally in a classroom, I will let the students do it together. So feel free, anytime you feel free to pause the video and try it out yourself before you keep moving. So basically, we got three forces, F1, F2, and F3 being applied to a rigid body. And then this one right here, again, vector addition. You cannot do simple algebraic addition. So you have F1, F2, and F3 together. So what you were doing over here is that you are going to break F1 into horizontal component, vertical component. We're going to break F2 into horizontal component, vertical component. And we're going to break F3 into horizontal component and the vertical component, okay? And then once you break them, remember we talked about the angle 3, 4, 5, you're doing the same thing. Once you break them individually, you're going to put all the I together, you put all the horizontal together by combining all the I component. Be careful with the sign, right? Horizontally to the left will be negative, to the right will be positive. And then you are also going to put all the Y component together. Again, be careful with the sign. Y component or the J component going up positive, coming down negative. Be very careful with the sign. And then afterwards, and then we have the resultant force overall X component, resultant force overall Y component. And then you can use Pythagorean theorem to calculate the diagonal, okay? And then you do your tangent inverse to find out the direction. How bad with you? So this is all I want to show you for chapter 2, section 2.1, 2.2, and 2.4. Thank you for watching the video today.